primarily the second moments of the estimators, though in fact the theorems that I shall state later enable you to discuss moments of any order, so that if you have an estimator which is a function of the moments of the sample data, then you can produce edge-with approximations under the conditions of our general theorems. I'll discuss towards the end of this lecture the first problem that I raised. That is that if we look at our second moments, they're generated by armor models, in other words, by dynamic econometric models. And so the second moments have not got the kind of properties that we discussed earlier. However, in one case, that is where we have classical static models, where the exogenous variables can be taken as non-stochastic, then the kind of theorems I was discussing last time are easily extended, because you still have that the second moments are obtained by taking the second moments that we would be primarily interested in are still taken by taking sums of the form zit ut upon t, where the ut can be taken as identically independently distributed, and the zit can simply be taken as constants, so that we then have a generalization of a central limit theorem to a case where we have weighted sums of identically distributed errors, and the extension of the central limit theorem and the corresponding extension of the edge-with approximation is relatively easy to work out. This is, I'm afraid, all I'm going to say about this. As I say later, I'll look at the cases where the zit may involve lagged endogenous variables, which is the case that we're primarily interested in. However, the other extension that I want to talk about is the extension in which you look at nonlinear transformations of such moments. In the literature, it's often the case that people look at multivariate cases, but in fact all my own work has been concerned with the single variate case, in other words, looking at the marginal distribution of a single estimator or a single test statistic. And my own notation in this field is that what one is looking at is an xt, which is given by square root of t, and then some general function, e, which stands for error, in fact. Here's the mnemonic there, qt. The vector q is a set of second moment variables, data second moments. But in fact, in my own work, I've used either of two assumptions. First of all, that the q can be split up into a normally distributed vector plus some extra second moments, which are typically the moments of the errors on the estimates, and which are therefore distributed in Wishart distributions. It's a joint Wishart distribution. Yes, in effect, PW is my usual notation. P are a set of normally distributed variables which may be of the form that I've already mentioned. That is, P might be some kind of vectorization of U prime Z matrix, where Z's are non-stochastic exogenous variables, then the u's are normally distributed variables. So in that case, you would have that the p's are jointly normally distributed. The w's, well, typically of the form again a suitable vectorization. There, of course, you'd only take the upper triangular part of the matrix to vectorize. And this would be an estimated error variance matrix. Now that's one set of assumptions that I've made. The other set of assumptions, this of course is not suitable for dealing with dynamic models. The other set of assumptions is simply that the Q vector can be approximated, its distribution function can be approximated by the multivariate generalization of the edge of distributions that I've discussed already. So let me mention very briefly what this multivariate generalization is. Of course, one can always think of an edge approximation as a generalization of an asymptotic distribution. And yes, in this context, I'm always going to assume that expectation Q equals 0. In other words, we always rescale so that Q is measured from its mean. And then what we're interested in is square root of TQ. In other words, we're assuming that Q is such that square root of T times Q has an asymptotic distribution. And then I write my asymptotic distributions with just a squiggle with an A underneath. And I certainly find it useful then to transform the Q's so that they have a unit variance in discussing multivariate Edgeworth distributions. So this is just a linear transformation on the Q's required. Well then, of course, the joint density function is going to be the usual form, just the sum, the exponential of the sum of the squares of the Q's. X minus a half Q prime Q form. And on the outside, 1 upon square root of 2 pi to the appropriate number, should we say, we have k elements in the Q vector. And as I did before, let's write this just I of Q now, little I of Q. Last time, little I was a scalar Q, for a scalar Q, but we'll write this for the multivariate Q. Well, then one can define various derivatives with respect to the elements of Q. As an example, d cubed d squared q1 d squared d q2 of I cubed. And find that these can always be written in the form IQ times by a polynomial, which is a multivariate Hermite polynomial when you take account of -1 to the 3 minus 1 to the 3 on the outside. The minus 1 always turns up the number of times you differentiate, total number of times you differentiate, to get the Hermite polynomial. I mean, that's just an arbitrary factor that I'm introducing to make the polynomial be of the standard form. I won't introduce notation for such a Hermite polynomial. I mean, a natural notation is just something like h21, because you differentiate it twice with respect to the first and once with respect to the second. Okay, so in that way you can define multivariate Hermite polynomials, and the general Edgeworth approximation is obtained by taking linear combination of such expressions, including, for example, a 0th order term, which would be usually IQ itself, and then first order terms which would involve only the first derivatives of IQ, second order terms involving the second derivatives, and so on, so that the rth order term would involve the rth order derivatives with respect to the elements of Q. So that is a general definition of an Edgeworth distribution, and with that definition, if the coefficient of IQ itself is 1, you find that the integral over the Q space is 1, so that it has at least one property of a probability density, that it adds up appropriately. But in generalization of my last remarks last week, it still has rather unfortunate properties on its tails. However, we can now regroup the terms that we have in this Edgeworth expansion, and for a valid expansion, what one needs is that the various terms are of appropriate order in t to the minus a half. And in fact, since the formulae are rather complicated, I won't, sorry, not t to the minus a half k, because I've got a k, but also I always say t to the minus a half r for various values of r. And what one tends to do is to regroup the terms so that various Hermite polynomials are grouped together which correspond to terms in the multivariate Edgeworth expansion which are have coefficients of various orders in t to the minus a half. And one says one has an rth order Edgeworth expansion if the highest order terms in the expansion are multiplied by coefficients of order t to the minus a half r. Now, of course, that doesn't tell you a great deal, because I haven't said how you're going to regroup the Edgeworth expansions so as to pick out those terms which should be of that order of magnitude. But I will, a little later, explain that a little bit more. At the moment, however, let me explain what the point is of this initial statement that I made, that we want to look at the functional relationship xt squared of t e q t, where q is a k minus 1 vector. What we require is, first of all, that eq equals 0, and then that q has in the limit a normal distribution. Q has an asymptotic normal distribution, which I've already stated. Then what we also require is that this is order 1 upon t, so that when we take our Taylor series expansion, we find that we've got xt equals E naught. Let me write this also E naught, rather convenient notation. Upon t, yes, let me write it E naught upon t. So that E naught, in fact, is just bounded as t goes to infinity. So when we now see what xt is, of course we've got E naught over square root of t, which means that it's going to be relatively negligible compared to the next terms, which we can write in the form EQ times Q multiplied by square root of t, plus further terms, which I'm going to discuss later. But let's look at this first term here, and of course notice that the further terms are at little o1, because they involve q squared q to the yes. Well, let's look at the remainder terms, perhaps. The remainder term can be taken to be d squared e dq dq primed at some intermediate point between q and the origin, multiplied by half, multiplied by q primed q, and then I'm afraid the whole thing is multiplied by square root of t, which I can put on the top here. Clearly, if we make the assumption that the second derivative is bounded for some region, some, in fact, small neighborhood surrounding the origin, and take account of the fact that square root of tq has an asymptotic distribution, meaning that q prime, q itself is of order t to the minus a half, then this product becomes t to the half multiplied by t to the minus 1, so of order t to the minus a half. Therefore, can be neglected when we look at the asymptotic distribution. Likewise, the first term here is of order t to the minus a half. So the only term that's going to be of order 1 is the second term, and that's a linear combination of asymptotically normally distributed variables, and therefore we'll have an asymptotic normal distribution. And in fact, on the assumption that I've made already, that q has q squared of t has a unit variance matrix, you're going to find that xt is asymptotically distributed, mean 0, and variance matrix given by this normal linear transformation linear transformation of a normal set of normally distributed variables, which is just eq prime dq upon t. Now, we don't actually need that the derivative is a constant. But what we need is that the limit of eq prime eq exists, and then we replace this by that limit as t goes to infinity. So we can write sigma squared equals limit t tends to infinity eq prime dq and sigma squared is then the asymptotic variance of xt. It's sometimes useful to have EQ depending on t, the way I've stated it here. Of course, the simplest case is to assume that E is a function that doesn't depend upon t, and that slightly simplifies the statement of a lot of these results. Well, so that's the asymptotic distribution. And then let me say a little bit more about what one needs to prove the validity of this type of result. I said that Q was required to have an Edgeworth a joint Edgeworth distribution, or that the Edgeworth approximation should be valid. In fact, the requirement for that, which is at first sight a little strong, is that if you look at the yes, I should be looking at eta s, which is log in other words, it's the cumulant generating function for the Q's. Now that is defined simply by taking the exponential of s prime times Q, where s prime is a vector of dimension k, and then taking the logarithm of the expectation. So that is what's called the cumulant generating function. And the requirement for the validity of our subsequent results is that if you differentiate with respect to the various s's, si, sj, etc., any number of the s's, and there are such s's, in other words, we're looking at an nth order derivative, that should be of order t to the minus r plus 1, in order that an nth order expansion is possible. I'll show you what an nth order expansion is later. Uniformly in some neighborhood of the origin. Now, in fact, this function is labeled a cumulant generating function because the derivatives at the origin are, in fact, the cumulants. So when we say that this has got to be uniformly bounded in some neighborhood of the origin, that will be sufficient to ensure that the corresponding cumulants are finite at the origin, because they are the derivatives at the origin. But you see, it's considerably stronger to require that they're actually bounded in some neighborhood of the origin uniformly in T. Of this order in T. This is simply the equivalent of saying if you multiply these by T to the R minus 1, that they are indeed bounded. This looks a little obscure at first, but you see the reason for it is that if you look at what T times Q is, it's something in the nature of a moment, and that means it's got T terms, and provided that the variance covariances between the various terms are finite in an appropriate way, then it's not surprising that you require that the moments themselves, or rather the cumulants that are connected with these moments. See, you're looking at something which is of the nature sigma y j equals 1 to t, where y may be a rather complicated function of the current data point, the teeth observations, and of course you haven't got independence. As we assumed last week, you have kind of time series dependence type properties, but it's not too surprising that then the rth cumulant of tq would be of order t. And then, of course, in order to get q, you're dividing by t, and you're dividing r times, in effect, because you're looking at an rth order kind of cumulant, and that gives you the t to the minus r plus 1 type of formulation. In fact, it is practically uniformly true that any moments derived from an ARMA model have this kind of property, that their cumulants behave in this way. But of course it requires proof. It requires looking at. Then another way of putting this is the following, that now if you look at the cumulants of t, square root of t times q, which you remember is the thing which has the asymptotic distribution, and call them kappa 1, kappa 2, etc., then you have the property that kappa 2 is finite, because square root of t times q has finite variance, that kappa 3 is ot to the minus a half, kappa 4 is ot to the minus 1, and so on. So in fact that kappa r is ot to the minus a half r minus 2. And this is in effect the result that we need in proving the order of magnitude of various terms in our expansion. Well, now, using as usual phi of s to mean expectation e to the s primed q. The next property, I think, is more easily seen in looking at, I'll call it phi star of s. It's very simply related to our previous one, because it's obtained by looking at the cumulant generating function for square root of t times q. I'm just reminding you of a well-known relationship, that is clearly the same as expectation, looks like it's exponential, square root of t s prime times q, and so it's just phi square root of t s. But the point is that it's phi star that tends to a limit, and that is because square root of t times q is asymptotically normally distributed, and in fact the limit as t goes to infinity is just exponential minus a half s times s, which is the characteristic function from the asymptotic distribution. So it's not too surprising that the next condition we require is one, I think really, a similar condition was first given by Chambers in a pioneering article, Biometrica 1967. Durbin, and the reason I mention that is because I and Steve Satchell have a forthcoming article in Econometric which uses the same condition, but in fact Durbin in 1980 succeeded in considerably reducing the condition, making it a much weaker condition. So let me quote Durbin's condition. Durbin looked at the region R, which is s prime s, which is just the exterior of a closed ball surrounding the origin, hypersphere surrounding the origin of radius square root of kt. So expanding with t to the half as t goes to the infinity. K being a constant greater than 0, rather arbitrary constant, no importance. And I ought to be using capital K to prevent confusion. Capital K. So then his condition is simply that our phi star s ds is O t to the minus half, and we have an extra 1 in there, I'm afraid. Now again, you can see that this is a condition that seems likely to be satisfied, because what you're doing is, first of all, that your phi star s is tending to a normal distribution of this kind of type, and then you're simply allowing the region that you're outside to expand, to cover the whole space, if you like. The region that you're outside is further and further out, and so you would expect that this condition would be satisfied. In effect, Durbin proved that it was satisfied in a simple autoregressive model, and one could easily extend that, I'm sure, to more general armor models than he was looking at. Steve Satchell and I have been showing that this condition is satisfied by general dynamic models, that is, autoregressive models with exogenous variables, provided ordinary stability conditions are satisfied and the errors are normally distributed. So in fact, this kind of condition is satisfied by the second moments of data generated by general dynamic models, dynamic economic models, where the errors are normally distributed. Of course, we were only looking at cases where the number of lags were finite in the endogenous variables and the exogenous variables. And those are the basic conditions. The two conditions on the derivatives of the cumulant generating function, and that the characteristic function goes to 0, if you like, sufficiently rapidly at infinity. And now let me look at what is actually involved in, first of all, deriving the Edgeworth approximations themselves and then proving that they're valid. What one is going to do is to work through the expression for the characteristic function of the E. And one can't really avoid working with characteristic functions as distinct from the moment generating functions. In other words, you have to work in the complex domain. You have to look at expressions of the form exponential I mu square root of t, sorry, not mu, square root of t, times by the E function, E q t. What one is going to do is to first of all prove that you can approximate this with a uniform bound on the error, provided that U lies in suitable regions. One is then going to integrate to get the inversion of this and prove that if you split the domain into a region surrounding the origin where the bound on the error in the characteristic function is uniform, that you can also neglect what happens outside the region, so that you can make the combined integral have a uniformly bounded error as t goes to infinity, a bound of the correct order of magnitude as t goes to infinity. So let us first of all look at the way that we approximate the characteristic function. And let me see if I've got all my brackets in place. I'm afraid I haven't. I need another one. So this is just the definition of the characteristic function for xt. This is just, perhaps I ought to say that all I'm doing is to look at exponential IU xt. The procedure goes then as follows, that we first of all approximate EQT by a Taylor series expansion about the origin. And I'll just label the remainder on that expansion R1. The little r means that we're taking r terms in the Taylor series expansion, and then capital R1 is the usual Taylor series expansion remainder. Clearly, in order to be able to do this, we need to be able to assume that the r plus 1th order derivatives exist. And and we're going to assume that they're uniformly bounded for Q lying within some neighborhood of the origin. The first point to make is that outside this neighborhood of the origin, we can neglect the errors if we simply take the two regions and split. What is going to happen outside this neighborhood is that when we take the integral of this expectation, because I is imaginary there. Of course, we have that the absolute value of the exp is 1, and so that all we have to worry about is what is the probability of being outside this region, and on the conditions we've given we can easily prove that what happens outside is negligible of order t to the minus half r plus 1. That is, of course, simply because the xt is of order square root of t on outside the origin, and therefore the probability of being outside a region of dimension proportional to square root of t is less than t to the minus half r plus 1 for any r. So all we need to do is to consider this Taylor series expansion within our neighbourhood, and within our neighbourhood we require that the derivatives are all finite that occur in this expansion. Then what we're going to do is to look at the first approximation. The first approximation is of the form, and I'll write it. The corresponding thing with ER in place of E. And then the next thing we're going to do is simply to retain R terms in the power series expansion for the exponential. So in other words, if we write this whole thing that we've got within these brackets as Z, then we're simply looking at the formula exp z sigma z to the s upon factorial s plus again a second remainder R2. Now, R2 we can deal with using a well-known inequality due to Feller, or at least quoted by Feller in his corresponding chapter on single variable work of this kind. And at this stage, I'm simply going to write f r u equals sigma s equals 0 to r z s factorial s, where the z is, as I said before, what we have in this formula here.
What's this inequality that deals with R2?
R2? Well, in fact, Feller has a slightly more complicated inequality than the one I'm quoting, which is the one given by Feller himself. But in this context, I mean, all that we need to note is that it's equal to R2 is equal to x z star z to the r plus 1 over r plus 1 z star is theta times z, and z is imaginary. So z star is also imaginary. So exponential z star has modulus less than 1, and so you simply get the inequality that is less than or equal to that. And then if you chase out and see what bounds you can put on z itself, you find that you can then make use of this inequality to show that switching from the xz to the FRU makes little difference. So this is makes a negligible difference. So this is the basic inequality that's used. It's used in a slightly different form by Durbin following Feller, because they are looking at the difference between xz and z star, should we say. They work it in this way, and they introduce a further term which depends upon z minus z star into this formula. They want to write down a formula for z, where z on this side is a z star, which is some approximation to z. And so they, as I say, they use a more complicated form. But this is the basic form that's really required. It's, in other words, a relatively simple kind of inequality that we're basically using here. And so my next thing that I'll use, I'll simply differentiate by not having an x on it, which is x f r u. Sorry, I'm getting myself confused. FRQ times I U square root of T. Now, I was right first time, so I suddenly went back on my tracks and confused myself. This is FRU, and the basic idea, you see, is you're making an expansion of this Taylor series. The Taylor series in itself yes, FRUQ. The first R terms that we had in the second expansion, the power series for the exponential, contains powers of u up to the rth order. So FRU depends upon u as a polynomial up to the rth order. But because at this stage we've already had a Taylor series expansion which gives you ER as a polynomial in Q, it's also a polynomial in Q. It's a polynomial in U and Q jointly. And of course what one can do is now to take the expectations of this polynomial in Q. This is an expectation with respect to Q. But now replacing the distribution of Q, the exact distribution of Q, by the edge of approximation. So that is the final stage, and that is this final approximation that we've got here is obtained by using the edge of the expansion rather than by using the well, this gives us our approximation for psi RU. And what we then have to do is to invert this by taking the usual inversion formula and integrating and again in the initial stage of making this approximation, I was using the idea that you can neglect what happens about some neighborhood of the origin by arguing that the errors are of sufficiently low order in t, and just look at what happens within some neighborhood of the origin. At this second stage, in which we invert again, we do the same kind of thing, now looking at what happens inside and what happens outside the region defined by capital R in my statement of the conditions for the theorem to be true. And the essential point of that second condition is that if that condition is satisfied, you can neglect what happens outside the region, in the region R, in other words, outside the region corresponding to the hypersphere defining R. Look only at what happens inside this region. And at that stage, use the uniform bound which you can establish initially on the order of magnitude of the error in this approximation. And therefore prove that if you simply invert this approximate characteristic function, you will get a valid approximation to the distribution of xt. Well, I'm aware that in an hour I've merely sketched something. I really haven't proved anything. But all I intended to do here was to give you an idea of what can be proved. And what can be proved is that if you, as in my Walras lecture, simply go ahead by using these approximations, integrating as though you had Edgeworth expansions, using some of the basic properties of characteristic functions, that is, that if you want to invert an expression which is of the form of some, say, s to the r times psi s ds, then I should be actually using psi t, because I want to be looking at characteristic functions. So we're looking at the case where we're inverting using some characteristic function. Then from the definition, this is overall values minus infinity to plus infinity in the single variable case, or more generally, if we're looking at a multivariate case, then this might involve powers of more than one element t, and we should be integrating over the whole Euclidean space of appropriate dimensions. then you have this kind of formula which I've quoted already, which involves the I times to the R times by the derivative d by dy to the R of the density f of y. Well, that sort of thing carries through in the multivariate case also. Actually, in my work where xt is being defined as just a scalar, then one is often making use of this kind of basic property. And what it does, you see, is to give you a formula whereby when you have polynomials here, you get results for distribution functions which involve derivatives of the kind of basic distribution function, and so again lead to Edgeworth type formulae for the final single variable distribution of xt. So one ends up with a formula that's of the Edgeworth type involving the derivatives of the e's, because they're what are determining what these approximations come to, and the cumulants of the original variables q. These formulae are, as you will find if you look in the literature, very complicated, involving the cumulants up to the fourth order, the derivatives up to usually the third order. Then you have, of course, the problem of whether it's possible to simplify these formulae, get reasonably simple formulae, when you actually look at the forms of the e functions and the relationship between these functions and the underlying distributions of the q's. And this very often happens, and I'll look at a particular case next week.